So in this lesson, we're going to talk about Numpy. Numpy is a library or a module for Python for doing numerical computations, and it gives you a set of data structures that are much like MATLAB, if you're used to that, where you can have an array and you can sort of operate on the entire array. So you can say add 1 to every entry in the array or something like that. And we'll show some examples of things like that. But what this allows you to do is have much faster computations for numerics in Python. So Python is slow because of something called, primarily because of something called duck typing, which is, also the real name would be dynamic typing. But the idea behind duck typing is if it looks like a duck, then it's a duck. So if you have a number and it looks like an integer, then it's an integer. If I have a number that looks like a floating point number, then it's a floating point number. And in order for the interpreter to figure this out at every time, every time you execute the code, there's some metadata around the variable that makes things slow. And that's why in compiled languages like C or Fortran or C++ or something like that, you actually have to indicate whether each variable, you have to define each variable, whether it's an integer or whether it's a floating point number. So what Numpy does is it gives you a set of data structures as objects, and of course everything in Python is an object, that have a single type. So the data structure would be like an array of floats or array of integers, and these are stored in memory in contiguous storage. And then it gives you a set of common functionality where two arrays can be multiplied, or an array can be, there's some operators are overloaded, like the plus. So you can take an array and you can plus 1 to it, for example, and it will add 1 to every entry of the array, and it does it in compiled C speed, essentially. And so, and that's because the implementations are done in C. And so it gives you a lot more faster ability to do computations much faster in Python. So let's look at some examples about how slow Python is. And so this was actually from the output of a Jupyter notebook. So you can just copy this from the slide right into the Jupyter notebook and run it if you want. But basically what this does is a pure Python implementation of creating a list of 1,000,000 numbers and adding 1 to each entry. And so then the Timeit module runs a series of loops and then does some averaging over to report the amount of time that takes. So in this case, you can see it took 110 milliseconds plus some standard deviation there. It did 7 runs, 10 loops each. Okay, so comparing that to Numpy, so here's the same command. I have to import the Numpy module. So every time you use Numpy, you have to run this import Numpy command at the top of the, once at the beginning of the notebook or at the beginning of the Python script. And so once it's loaded into the namespace, and then you can call this function. And what this function does is it also creates the array of 1,000,000 numbers. So 1, 2, 3, 4, 5, 6, 7, all the way to 1,000,000. And then it adds 1 to it. And you can see here that there's basically an order of magnitude difference. So the Numpy implementation is about an order of magnitude faster than the pure Python implementation. There's also the ability to call functions on entire arrays. So again, here's an example and some timings. In pure Python, I can import the math library, and the math library gives me access to a function called sign. So if I then call sign, the sign of 1, the sign of 2, the sign of 3, and I square that every time all the way to 1,000,000, create that list, then you see 322 milliseconds versus the same operation in Numpy. So here I'm calling, I create the array with this command. So this is array 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way to 1,000,000. And then I just call the sign function on the entire array. And then I square what appears to be the entire array, but of course what I'm doing here is squaring every entry in the array. So these produce the exact same result, and again, order of magnitude faster, more than an order of magnitude faster in the Numpy implementation. So Numpy offers several built-in functions for creating arrays. So you can use the Numpy array command where you can just say stick in 3 integers, and again, because they look like integers, this will be interpreted as an integer array. Okay. Likewise, here I have basically complex numbers. The J indicates a complex number. So this is going to be interpreted as a complex array and stored as such. I can create a range of numbers. So in this case, I'm creating a range of numbers between -10 and 10. I'm taking steps of 2 in doing that. And here, even though I've only written integers, notice there's no decimal points here, so they don't look like floating point numbers. But then I can go ahead and specify the type, in this case, a floating point number. So this will give me an array between -10 and 10 of floating point numbers. I can also create a len space, a linear space, so this is going to go between 1 and 4, so it's going to give me, those will be the endpoints, 1 and 4, and it's going to give me 6 numbers total, so 1 and 4 in between. Right? I can create indice array, so this would just be a 3x3 array that would have 0, 1, 2, 0, 1, 2, 0, 1, 2, just a list of indices. And then also I can create something from a file. So if I have a file that's stored, an array that's stored in a file, then I can read it in. So it gives you several ways to create arrays in that fashion. So again, these were created with actual, these outputs were created by actually running these commands in the Jupyter Notebook. So often, just so we don't have to type out NumPy every time, a lot of times what we'll do is we'll say import NumPy as NP, just to shorten what we have to type every time. So this is just shorthand so that we're loading NumPy as NP. And then here we create use an arange to create a list from 0 to 9, well, 0, 1, 2, 3 to 8, 9 entries. And then we reshape it into essentially a 3x3 matrix, and then there's the output. Likewise, then we can use the similar syntax to MATLAB. So what this is saying is take the entire first column. That's what the colon means. Take the entire first column for the 0 indexed. I'm sorry. Let me speak again. Take the entire first column of 0 index, right? So the 0, 3, 6, 0, 3, 6, right? I can report the shape again. So since everything's an object, these arrays are objects, therefore X is an object. So then I can call, it has an attribute shape, and the shape here is 3x3. Can also do some fancy slicing. So basically what this means is I'm reassigning, I'm taking every 2 entries, right? So I'm saying from the beginning to the end, in both rows and columns, take every 2 entries. And you can see there I have 0, 2, and 6 and 8. So I've taken basically the corners, so you can do this kind of fancy slicing like that. And then I could, for example, reassign the first entry, the 0, 0 entry of the Y array to 100, and I just output it there, and you see that. So you can do things like efficient and effective compact finite differences, which we'll use a lot in this class, finite differences. So basically, if I have an array X, then Y is just that array squared, and I want to compute the derivative dy dx. Well, then I can just do it this way, where I have essentially what this says is from the second entry, right? So 1 from the second entry to the end, minus from the first entry to the -1 entry, so 1 from the end. So this is from the second entry to the end, subtracting the first entry to 1 from the end, right? So that basically gives me the difference between every 2 consecutive elements in the array. And do that for both Y and X. That's basically delta Y over delta X. That's an estimate to the derivative, right? So it's a one-line way to compute the derivative of the entire array, right? And of course, this would be, since this is a quadratic, the derivative should be something like a straight line, right? The last thing is you can do kind of sophisticated broadcasting. So broadcasting is basically when you can multiply entire rows over an array in a certain way. And so here what I've done is I've created 3 random arrays, red, blue, and green, all of them that are 800 by 600. So this would be like, for example, images, pixel images. Then I can combine those arrays into a bigger array, right? And so the shape of that bigger array is 3 by 800 by 600. So then I can multiply that by essentially an array of 1/2, 1/2, 1/2. So this is going to multiply across the first indice, right, 3. And it's going to multiply across the first indice 3. And basically what this is going to do is cut every number that I originally, all of the red, green, and blue numbers, it's going to cut them in half, right? So it's going to cut them in half, and it's going to do it all in one operation. So this is kind of a fancy way to do very kind of sophisticated calculations. And of course, this is this happens in compiled C code, so it's very, very fast, right? So the best way, of course, to learn NumPy, like any language, is to practice with it, and so that's what we're going to be, we'll be using throughout the course, and you'll pick up a lot more information about it.